Oh yeah, I'm going to be in your robotics class next semester. I said in the long run I want to do AI research.
Cool. Is Lynn all set?
Lynn is all set.
Okay.
We are live.
I'll pick you up, yeah.
So
Thanks everybody for being here. This is Mark Sherman's proposal defense. As he was mentioning a few minutes ago, this is where input is really valued. Input will be valued at the final thesis defense, but here it's much more actionable. So thanks for being here. So the format is Mark is going to give his presentation in about a half an hour. And then we'll do questions from the audience here first. And then the committee will have questions. I'd like to thank Jay McCarthy for being one of Mark's readers. And Franklin Turback. Lynn, are you there at Wellesley College? Does he have a bidirectional link?
Yes, I'm here. I keep on having trouble.
Hear you. Thanks, Lynn. Thanks for being here. Take it away, Mark.
okay, hi. Thank you again for coming. And again, this is a proposal, and you get to come back hopefully in a bunch of weeks and see this in its final form based on what we're going to discuss today. So let's jump in. We are going to be talking about learning analytics for block-based programming. The language that everything's on is App Inventor, and I'm going to step through everything here. Learning analytics is able to, the area of study where we look at what people are doing while they're learning, while they're trying to develop something. In programming analytics, it's really fun because we have code, which is something you can measure very easily. Your entire thought process is represented through that code somehow. And learning analytics is sort of the way that we're trying to get into what are those thoughts that are happening that result in the code that you see. So the whole core of why we're here and what I'm trying to do is I'm trying to convince you that there exists a pattern that can be detected in code that you can see that can detect when a student is flailing, when a student needs help. So let's unpack this a little bit. Their flailing behavior is something that I'm going to say a lot. This is very close to other behaviors that are in literature, such as tinkering, such as moving, depending on the paper you do. But basically anything that's unproductive, sometimes random, and it's an indication that the student is lost, indication that the student needs help in whatever they're doing. Imagine a classroom scenario. They have 40 minutes. Here's the thing they're trying to get done. They're trying to get through this learning process. And whom do you help? You have limited resources. The goal here is to be able to, in the end, have a tool that can detect who currently needs your help and who there, so you can judiciously use your time in the classroom to find those kids. Because every study shows they don't volunteer that knowledge. They may not know that they're lost, but this will help figure that out. That's the goal. And that's why I use the word flailing, because it encompasses a bunch of different behaviors that may indicate that. It's really similar to some other things. It's really close to Perkins's idea of tinkering, but it's not quite, because it's just whatever is in service of the I need help bit is what we're trying to detect. But what's interesting is what looks like flailing could be discovery, trial and error. So there is definitely healthy tinkering in Perkins's work where the person is trying stuff and failing at it, and that's good. But somewhere there is a line where they're trying stuff and it never becomes good. And they are so far off that path, the way Perkins actually writes on it is they're fighting their way up the wrong hill. And they need to completely come back down and find a new hill, and they can't tell. And this is sort of, that's part of the mission of what we're trying to detect. So where is the line that I can say this pattern is good enough, this pattern might need help, or how do we even describe what that line can be? So first, let's talk a little bit about App Inventor, take ourselves back. In case you haven't seen it, App Inventor, a beautiful web-based app development environment. You can grab stuff from over here and drag it over here into the middle, and you can build your app. This is a fairly sophisticated app that I that I built a while ago just to show you that it's showing you a visual representation of the app in the middle, and the code looks like this. It is entirely block-based. It's this beautiful, colorful, things snapped together system that is a really interesting language unto itself. And this is the language. You often see, well, what's the code underneath it that it represents? There isn't any. I mean, there's a text representation of what you're seeing on the screen because like the computer's rendering it, but that's not really human readable, writable. This is the language. The language is these little bunches of code blocks. And that makes it really interesting for study because not only can you assemble expressions, you can physically move them around. And I think that's going to be a big indicator in what we're looking for. So our approach of what we're trying to do is we're going to build fine-grained instrumentation into App Inventor. Actually, I already did. Develop and run activities with kids that elicit these kind of behaviors, and we did. And then we collect snapshots as they code. And then we look for patterns in those snapshots. And I'm going to unpack that as we go. The whole point of the talk basically is unpacking this slide. So first, the participants. They were middle school kids, grades 6 to 8. They're already in a research program called CS Pathways that we're running here. That is Professor Martin's program, where they are learning App Inventor in class or in a summer camp. And it's being added to an existing curriculum that they already have. So these kids are already sort of like one step up, level 1 bootstrapped. I typically see them at the very beginning of their experience, so level 0.08 maybe bootstrapped. And our study was conducted both in formal in-class environment and in the summer camp informal environment. There are 2 cities, 4 classrooms, 3 teachers, 2 summer camps. There's a reasonable amount of diversity in this population that totals 127 participants. So it's not one class on one day happened to show this and they all were tired because it was right before lunch. Like there was enough variation that it's not too specific. Protocols. So there were 2 activities that were run. One was the debugging activity, the other was the temperature activity. The debugging activity happened in classrooms and in the summer camp. The temperature activity only happened in the summer camp. It was a brand new activity. We threw it in. And that actually is pretty interesting, and we'll get to that in a little bit. Here's what the debugging activity looked like. Here's the app. It is it's based on the Talk to Me app, which is like the intro app for App Inventor that we use. It's the Hello World of App Inventor now, where it's a slightly more sophisticated version, but they've basically seen this. Even if it was a day ago or a week ago, they've seen this concept, and they've seen the code behind it. And what I did was I broke it. I made this app and I said, the front panel is correct. The screen is all right, but there are 3 bugs that I charge you to fix. And it was their job to identify and fix these bugs. Why do a debugging app? Debugging is a great way to access internal thought processes and get a gradient measure of competency with the code, pile of literature resources to support that sentence that you can read about in the document. Anyway, so that's what it looked like. The basic idea is if you shake the tablet or the device, it should say, stop shaking me. If you press the button, it should speak whatever you type in here as a user. And as a user, you can type in here and hit the button, and it should say that out loud. And then the bonus level, the third and hardest one, was update this label to also say whatever was said aloud last. So change it so it's also visually seen on the screen. That one was the harder end. This is what the starter code looked like. This is the code I gave them. So when the accelerometer sensor is shaken, it will execute this code, which is text-to-speech, speak, the wheels on the bus, which is not stop shaking me. So the answer to that is really simple. You just change the word to be stop shaking me, and bam, you fix bug number 1. Bug number 2 is right now when you press the button, it will always say the same thing, which is hello student is hard-coded right there. You need to access that variable that is the user input to get it. And the answer looks like that. So they pop out, how are you, pop in the user input box, and then they solve number 2. I'm not going to show you number 3 just for time. So the other activity is the temperature activity. It's a quick Fahrenheit to Celsius converter. You type in a number in Fahrenheit, and it changes this text to be that temperature in Celsius. The code that I gave them to start, I built up a little bit of a little bit of platform for them, so they only had this procedure to modify. Right now, it would just copy Fahrenheit into Celsius. This is a straight copy. This is the solution. This is what's expected. And it's the formula to get from Fahrenheit to Celsius. The point of this was for them not to debug, but to build an expression, to build a compound mathematical expression, so we could see how they get in there and the order and the ways they put expressions together. And actually, expression building as a measure of expert user dub is already in the future work section and going to happen someday, because that's great stuff. We didn't do it in this study, but definitely showed that it's possible. So I'm excited about that, but that's for later. Anyway, this activity was actually really hard for a very beginner student. It did not have the scaffolding that the other activity had. We did not do as good of a job setting it up and explaining what was being expected of them. So a lot of students really had trouble with this, which at the time felt like a bad thing. And then coming back to analysis, where we're trying to detect flailing behaviors, we have a whole class of flailing behaviors because nobody understood the assignment. Some kids did though, so we can prove that those weren't flailing. It's gonna be great. Anyway, so how do we instrument it? Those are the activities that we're gonna do, that we did with the kids. We have kids. How do we actually measure what they're doing? So in the past, not in the past, every day, how do you typically see, you see a program when it's done. A student in any class works on their homework assignment, they hand you the assignment, and you only see the final artifact. You do not see the process that they went through to get there. And that's what's all the rage now, is instrumenting the environment itself to give you that history of what happened, change by change, blow by blow, to watch that app develop. And what I have is a system in App Inventor that allows any change to the program to be detected, and it captures the entire state of the program on every single change. You drag a little block, even if it doesn't change meaning, you just move it a little bit, and it's a little out of alignment. Every single change is captured. They fall into a few important categories. Was the block moved in space? Because if you move a block in space, it doesn't change the program. It just changes what it looks like to you. That secondary notation of organization and layout is important to you as a programmer, but doesn't make any computational difference. If this block is here, or if this block is here on the workspace, it doesn't matter. But a block can change context. I can pop this block out. This is now computationally different. I took a literal out of an input. That function can't run now. It's now computationally different. So that kind of change is not only captured, but detectable. I could also detect if text fields change, blocks are added or deleted, any other property change of those components we saw earlier, and really any other. I put a star on this because I capture the entire state of the program on every single modification. So it's possible to go back and mine for changes that we didn't even anticipate, because I can diff the entire program A to B at any given moment. But these are the important classes of change. Let's see, anything else? And what we do is we call this a snapshot that's taken on every single change. That's the word I'm going to be using from here on out. Almost 10,000 snapshots later, over 154 projects, 400 megabytes of Git directories, we have data. There are lots of things here. These are some basic, interesting descriptive statistics. Average was 70 snapshots per project. These are half-hour activities. Those activities I showed you took on average 70. Now, of course, this is heavily left-tailed. So that average is brought up by the fact that some people took like 300 changes over the entire half hour. But that's exactly the kind of stuff we're looking for. Median was around 65. Most snapshots on a project was 316. And the median completing time was about 20 minutes for a half-hour targeted activity. So that all sounds right. That all sounds like I am looking at what really happened in reality. So that sounds good. What I've done is I've built up all those tools. So all those features I told you about, different kinds of changes, those are extractable. We can see the blocks play back visually as the students saw it. All the tools are there, and I've started some analysis. And now we're going to talk about what's left to do. Again, this is a proposal. So what I propose is to use all those things to come to our conclusion of that pattern does exist to detect flailing. That pattern is detectable. And yes, an algorithm can be written for it that can be applied to a real-time device. Keep in mind, that is our mission, that is our goal. So the plan from here on out, you're gonna do, when I need to find the ground truth of who's been flailing. We collected data in a lot of places in a lot of time. We were not able to sit down with every student immediately after the activity and do a 10-minute in-depth interview about how confident they were in their work to know who to look for. So we actually have to deduce who was flailing if we're going to try to do data mining. We need to know what that truth is. And how we do that, I'll cover on the next slide. What I can do is I can count types of changes, start really easy. How many changes were there? How many changes were there that didn't change the abstract syntax tree, that didn't change the program, but did change the visual layout? I think that ratio is going to be very important. That's my core hypothesis is the ratio of visual but not programmatic changes to programmatic changes is going to be a thing. That's one of my big hypotheses going in. But when I have all these measures, so I can extract the features, those particular changes, I can then meta-abstract measures to that, how many features over time intervals. Everything is time-stamped, so I can say how long since the last thing, what was the average, anything we want to mutate that data around, all the tools are there and I can do it. And I've done some fun things. Can then run it through a good old-fashioned ANOVA, an analysis of variance, to say, all right, what dimensions that I've extracted in the previous steps correlate with our two populations. So if we know the ground truth of who's flailing, population A are heavy flailers, population B are light flailers, and maybe I cut out the middle population for that particular analysis and say, go, what things stick as a difference? What actually matters between these two populations? That's how a lot of research statistics get happened, good old analysis of variance. Then we get into the more fun stuff. Once we know what things are important, we can take all those features and all those different descriptors and do some k-means clustering on them, where we say what are groups that as humans we may not predict what is actually going to be important. There's a lot of research here that comes out of Stanford, because the Stanford AI lab has been on a cool education data mining bend for the last couple of years, and actually the instrumentation is heavily based on one of their early projects from 2012. And one of their big papers said k-means is all you need. K-means is a entry-level data mining technique. They did crazy harder stuff, and it didn't give any better results for taking learning analytics dimensions and extracting what correlated to a student who knew what they were doing versus not. Nothing beat k-means, no matter how many more hours of computation time you threw at it. So that's where I'm going first. And the result is what features, what dimensions affect this flailing property and how. Of course, that is predicated on knowing who's flailing, how hard. And this is the core of what's left to do between now and the final work. How is this assessed? How is this documented? How do I know this is right? And there are three ways to do it. 4 bullet points, but 3 ways. One of them is degree of success in the activity. These activities have right and wrong answers. So it's very easy to tell, did they get the question right? And that's great because that is purely quantitative. And actually the debugging activity, we have a well-developed rubric that actually breaks out problem 2 into 2 different classes. We have 4 or 5 degrees of sophistication in their solution, already rubriced, that's already been tested, that's already been validated. So we have a very rich dimension in the debugging activity of how correct they were. So that's one indicator. So if nothing else, maybe we don't know flailing, but maybe we can do like the Stanford team did and say, we can at least connect it to, did they get it right or not? And then that asks the next generation of questions of why. I think we can go after the why from where we are, because we also can look at their playback. We can look at, and I'm going to show it to you in a few minutes. You can look at their code moving around as they saw it, as they did it. And as a teacher, you can easily watch it and go, well, this is going nowhere. And so the plan here is to do expert analysis of this playback with coders. And we can do the same thing for the worksheets they turned in. All these activities I didn't mention earlier had a worksheet with them where they reported on what they did. They had pointed questions. It was a 1-page worksheet. I didn't get to do an interview with them, but but I did get a worksheet out of all of them. And that can be coded for student confidence and for solutions being properly identified and discussed. And that's also been a validated instrument. And there's a very, very small list, the last source of data, there's a very small list of students for whom we knew where they were. This is not huge, but it's a couple pilot people where we knew this person absolutely had full confidence in the activity. We knew this particular person had no idea what was going on. Very small list, not useful for aggregate analysis, but sort of for pointing us in the right direction. We can pull those out. So this is my plan for establishing ground truth. And of course, this has to introduce independent variables, different from the data. And that's what most of this is. This one is looking at the data a different way through expert analysis. So we have qualitative and quantitative in there. So preliminary examples, this is the part where I riskily exit the slideshow and start to show you some code snapshots in real life. And so here's the starter code for the debug activity. This is a student whom I extracted as a low flailing factor. This person basically nailed it. And I have no idea who this person is. Everything was de-identified at the server when it came in. So everybody's code named. No idea who this was or when they were. I do know they're a student. I filtered for that. This isn't Farzine running the test. I would expect you to nail it. I'm just saying. All right, so this is the starter code, and the first thing they do is they just deleted that wrong piece of text outright. Like already a bold move in step 1, which was like 3 seconds in. And you can see they pulled in the user input. This says background color. This isn't quite the right block, but that's a pull down, and you can select it to be the text property of that input. So this will now tell you white. It'll tell you, or none, the background color, if you were to run it. And then they changed it to text. So they got there really fast. And here's snapshot 5, the 5th move. This is like watching chess masters sometimes. Like the 5th move. They're now going after, what is changing here? I think they're just nudging the blocks around. And stop shaking me. There they are. And then they just kind of nudged them closer together to be prettier. So that was a very expert approach to it from a student. I have another example. There are many more snapshots. I'm not going to walk you through the entire history of it, but I'm going to start you here where they sort of know the user input is necessary. And that's why I chose this one, because it's sort of interesting that they knew it was involved and they tried to figure out how. They took the text block out of the one that wanted a literal text block. This one doesn't use the variable. That one's just supposed to say stop shaking me as a constant. That's it. And then they bring the user enabled. So that's going to say true. Was the user input enabled? Well, yes, it was. That will return true. So if you shake it, it will say true. And the kid's going, why does it say true? There's actually a period later on as we walk through these where it looks like, I can't say definitively, but it looks like the student is testing, because there are lots of non-changes that are happening despite there being changes in the project. And I think that was the student testing it, wiggling it, testing it, wiggling it. And that itself might be a huge indicator that I had no prediction of until I started actually walking through the raw data. So there's still like, just nothing has computationally changed in a long time at this point. But stuff is getting moved. Oh, there's another text box user input enabled. They duplicated that block. Okay, all right, getting there, but now I believe we're at about 8 minutes in for the student now, if I'm remembering correctly. So they're working their way through. Okay, and then they pulled a whole new event in. I don't want to spend too much time, but they then tried to solve the step 3, the hardest bug, when they had not yet solved the first 2. And that's why they introduced a new event. They're trying to find a way to do that 3rd action, which doesn't involve a new event at all. This is not the right way to do it, but it is indicative to me that they're trying to solve problem 3. And because there's the said last label, there's the key to problem 3. It belongs over here. But they're trying, despite not having solved the first 2, because both of them will say true and not the text that's desired. And they kind of hack around with this for a while. And at one point they duplicate the speak button event handler, and you can only have one event handler per event. which is a good rule, because otherwise it wouldn't know what to do. Luckily, it sends up a little alert flag and says, nope, that's wrong. You can't do that. So they bopped right off. And actually, that question of what do people do when they see error, that was the master's work of Benjamin G. at MIT recently, was basically about that. What do you do when you see an error? So he has a lot of writing on that. This kid figured out that it was wrong and he moved it. He moved it off screen. That actually wasn't visible in the porthole. So he moved it off screen. I say he, I don't know. And then eventually figured out to delete it. There we go. And now we're back where we were about 10 snapshots ago. So this is more flailing-y. And I'm going to rate them on a degree scale. You might be asking, did this person eventually get it? And the answer is yes. But this was a long time later, and it had some long pauses in between snapshots. So part of the data processing I'm doing is identifying the key window, which is the most right place to look. And I'm thinking the first half, the first 15 minutes is all I really need to look at, because the researchers, the teachers, the helpers in the room were allowed to start giving help after halfway. So a lot of people started having 2-3 minute gaps, and then suddenly blocks started flying together. But if I really want to know how they did, only that first 15 minutes looks like it's going to be useful. And that's also a new discovery that wasn't expected, though totally should have been expected. Actually, the very end is interesting because at one point they said, hello, I'm, and he wrote his name there, and I blanked it out. So when you shake it, it would say, hello, I'm Max, which isn't the kid's name. And then at the very end, changed it to stop shaking me, and then changed it back to say his name. So technically it's correct, and then 2 minutes later it's like, no, I'm still Max. Still not the kid's real name. All right, so that's where we are. Real quick, I want to acknowledge some people and some things. The National Science Foundation funded this in my previous work. Special thanks to a lot of people. Some of you were here. Thank you very much. My system testers who beat on my system to make sure it was sufficiently performant to handle the task. And of course, Fred, thank you so much. Jay and Lynn, my dad's here. So thank you to my parents. My wife Stacy's here. Everybody who supported me, everybody who's here, thank you for coming at 9 in the morning on a Tuesday to come listen to me talk about code block snapshots. And with that, I open it up to questions and discussion, which I hope will be good because I have more questions than answers at this point. So thank you. Lynn, you still there?
Yes.
Okay. All right. Yes.
All right, so are you judging whether or not they're correct by how many snapshots there are and the degree of success in each snapshot?
The degree of success in the project is judged by the final state. So it's as if they turned it in at the end. And I actually built a quick function in my viewer to be like, just show me the last one. And the last one shows you if they got there or not eventually. So,
do you have built into your system to know at each snapshot if it's computationally functional even?
yes. Oh, if it works.
Yeah, so I mean like
That's interesting.
2 event handlers, or there were blocks that were disconnected so they don't run. Do you have it set that your snapshot server will automatically detect this is a non-working state?
So it does not have a linter or a compiler kind of thing. Way back when, an earlier version of this, what I was actually going to be doing is running the App Inventor code through the generator that builds the executable code, and that generator would have been able to say this doesn't work. But no, I don't do that. So I don't know if at any point program automatically if the code is good. In App Inventor, though, it's very easy. It's hard to say it doesn't work. Because in this case here, App Inventor simply ignores things that have incomplete inputs. It just won't run them. So everything automatically becomes commented out if it's incomplete. So it's very hard to generate code that is programmatically incorrect because the system automatically says, I'll just go without. So it's hard to do, and I didn't.
Did I understand you correctly saying that there's only one way to do it correctly?
To solve these problems.
Yeah.
There is not one way, particularly in the debug activity. There is more than one way you could implement like that last label being updated. I showed the easiest to parse as someone who hasn't been studying this for like 8 months way.
People actually do the other ways.
There are a few different ways that I've seen it done.
One thing that you could do is that you could just like write down all the solutions and then just compute like the graph isomorphism between what they have and what the correct solution is.
Oh yeah,
Relatively small space.
yeah, and I do have the graph extractors written that can just generate a good old fashioned tree and do a tree distance compare. I'm gonna write that one down.
Well, the thing is, there are an infinite number of technically correct solutions. There are only a finite number of ones that are efficient. Because you could make a thing that adds one, subtracts one, adds one, subtracts one for an infinite number of times, and then prints out, this thing minus 32.
Right. So what's really cool?
But they only have 200 examples.
I only have 200 examples, and they only had 20 to 30 minutes.
Yeah.
So having spot checked a lot of it, basically everybody is doing one of 3 possible answers, with the vast majority doing number 1. Yes, that's possible. And if it was a homework assignment, knowing from the previous work that like Daryl Littman did on learning analytics and in undergraduate homework assignments, you see some crazy stuff, like people trying to defeat the system in an asinine way. Like actually there's a whole paper that I cited written about that, like when you're trying to defeat the system. That works, but they won't like it. It doesn't appear to be a concern here because of the time constraint on the activity. You had your hand up first. I'm sorry, I'll get back.
You mentioned that you would like to do k-means because k-means is a great way to do clustering in this case.
Yes.
You also mentioned that you have qualitative as well as quantitative data.
Yes.
The concern here is maybe you may like to consider another better method for this, because since you have qualitative or categorical data, k-means doesn't work here. So you would rather use the LCA, latent class clustering, rather than k-means.
Okay, that is great. K-means is the one that comes to the top. My plan, I can tell you what my plan was, and then you can tell me how right or wrong that is, and maybe we can talk later on that. The qualitative data is being used to identify, basically that's all the qualitative data that's in that little cloud of like how good were they, how flailing were they, gets reduced to a numeric dimension. And
what is done is clustering. We have 2 sets of variables, one for clustering and another for finding the profiling information. So if the clustering variables have quite a categorical or qualitative kind of data, then you can do k-means. You would rather do the means.
Okay. I would love to talk to you about this right after.
Oh, sure.
Once we go offline, because this is some wisdom that I would love to. The papers don't talk back when you ask them questions, so thank you. We have a queue actually.
Yeah. So just to clarify, maybe because I've read part of the proposal. So the goal of this, though, when you're detecting flailing, so is the idea that you want to be able to interject, like when flailing is happening? Because a lot of this, the analysis is sort of after the fact, right? So like, okay, we actually knew after all these kids are done that they were flailing, which is nice to know, but if the goal is to know how or when to interject, if I'm correct.
Yes.
So I think an interesting thing that might be worth looking at is doing something like you could do like a hidden Markov or something along those lines of the event. So like if a kid does something, right, do we know if they're flailing or not? Right, so there's nothing there, obviously, that is the flailing act, right? But something that looks at, there's something that you want to do here that gives you event by event analysis of what people are doing, so that you could say that at any point in time, is this person flailing?
That is exactly the end.
Right.
The end goal of it.
Right, and so I mean, as you know, I've done something similar, but not in this environment. I don't know if I ever sent you the paper, but I'm happy to, where we look at productive versus unproductive tinkering in an open-ended, like,
engineering style sort of environment. It was sort of programming, but not really. But yeah, we basically used, it's building blocks, they build circuits with blocks on a multi-touch table. And any block or circuit they make, are they productive or not? And so we found a really interesting way of doing this, and because we wanted to do something very similar, which is actually know when kids are being, we called it sustained unproductivity in their tinkering, right? If they're just doing the same things again and again and again and not getting anywhere in it, right? And we needed a way to understand it that was actionable, right? Because basically, similar idea to what you had, which was, let's look after the fact on a whole bunch of people, but the goal is that if we do this again, right, that we know whether somebody's flailing, right? So a good, at least worked for us. We looked at sequential pattern mining, and we found that, at least for our thing, it didn't work because there's just so much going on. That might be something that might work because your environment's a little more closed in terms of the task. But that's one thing to look at, that when you start to see patterns, because you are sort of seeing stuff. I don't know, I haven't seen all 200, but you might see something along those lines, that people who flail tend to have this sort of pattern, but there's a lot of variance. So, but another one might be looking at sort of again, this idea of looking at a hidden Markov, where you basically say that at any one point in time, if they're doing something, what's the likelihood that that is a flailing or not? And then one thing that might be worth it is not one instance that's flailing, right? Because you might flail for a second, or it might be a false positive, but sustained flailing, right? So I think, we might look at the person who was very successful and they did one little tweak or something, and that might come off, but the other person who had 30 blocks of a whole bunch of stuff, it's like, if somebody's flailing over a period of time over n events, then probably what you want to do is let somebody know.
Yeah.
Right. And so looking at something like that, once you have this data and going over 200's probably enough to start getting a sense of that n is big enough. And you might want to look at something like hand code 15 or 20 of the students, and then to build up your emission table or something like that, and then test it over the whole thing, and then go back and say like, okay, we built a model, right, that says whether people are flailing or not. We built up the model using hand coding, then ran it through the other 180, right? And how accurate was it, right? Can you start to do that? I mean, I'm adding more, I'm sorry.
No. Well, you've described pretty much exactly what I actually want to do, but didn't write down. Mike Tissamone, everybody. And what I would do, so what that gets me thinking about is, so one of the core pieces of literature that I have years of reading through and basing on is modeling student programming, Peach 2012 it was the best paper at 60 2012, where they did this kind of instrumentation on a Carol the Robot kind of super constrained problem. And then what they did was they used that, they used some clustering and they did some hidden Markov modeling, and they built this state transition diagram for the assignment. And it had bubbles that changed size depending on how often a student was there. Problems with it was that was aggregate over the entire population. No, they couldn't do it for a student yet. But that's exactly the kind of thing of build up the training data with like the hand-coded stuff, and then run it back and then try to build the model up and see how close you can get. But the point of being able to identify a student flailing at any point live while they're doing it, I think is actually going to go back to that idea of that state transition table. That if you find yourself going through a state over and over and over again, which is accessible because you have the HMM telling you what state you're probably in within a confidence, then you can throw that flag up. Now, what I didn't expect is that analysis was going to come back. I looked at it when I read it and said, that's like totally worked for them to do this. I'm trying to do a different thing. Because in looking at the data in the hand coding so far, one of the key things that's telling me this is one that I want to mark as a flailing is repetition of state. You end up back where you were before. So that's a huge feature that I did not see coming. And now that you've said that, I think that's the direction to go to capture that, to build a model that encompasses that, if I'm reading all these things correctly.
Hey, Mark?
Yes, Lynn.
Can I ask a question, or are there?
No, go for it.
So, in terms of marking your ground truth, and was it Mike who was just talking?
That was Mike.
Hi, Mike. So, are you going to annotate particular snapshots as being flailing or non-flailing? Are you going to annotate segments of snapshots as indicating flailing? I mean, what is it that you're actually annotating in terms of ground truth?
I was going to annotate on the project or time segments with the project, like dividing into quartiles. So it would be segments of time that I would judge as flailing or not. Depending on how many, which one of those I do is depending on how many I wanted to get hand coded, because hand coding by segment, multiplies the workload on my poor raters, who will be me and some other people. So I was not planning on coding snapshots individually for their degree of flail.
Okay, great. That's helpful. But I think the segments might be helpful, even though it's a lot of work.
Yeah, I think so too. It's something that I've been like turning over in my head of like, I don't want to, but I should.
How many guys were there in total? I'm sorry, I know it was on the first slide. I don't remember.
How many individual snapshots? 9,800 something, which is not enormous.
If I could just jump in. Mark,
Yes, right.
Near the end of your presentation, you mentioned how at the last few minutes, people like myself or yourself or Farzeen might have been walking around helping the kids. So
Yes.
you have to remove those segments.
That's all getting snapped off. That's why I think I'm just going to say first 15 minutes, call it that. Everything else is just ignored. Because I'm also having trouble with multiple sessions that a student there's nothing stopping the student from opening the same project up later. And then all of a sudden I have a change that's like 28 hours since the previous change. And App Inventor does some interesting things when you reopen on a second session that totally messes with the data. It renumbers the blocks apparently on load. But that needs to get filtered out anyway. So I've built the tool to snip off the end of histories.
Lynn, do you have a follow-up?
No, I have many other things to ask, but in terms of establishing ground truth and flailing, that was what I wanted to hear.
Go to Jay next.
Yes, Jay.
During your ground truthing process, you have an internal idea about what constitutes flailing, but you mentioned earlier as being like an expert system. And what your goal is to encode that process that you are thinking about. Now, you talked a lot about some statistical ways of doing that, but do you also have a theory of what represents flailing? That's question number one. And then kind of a follow-up to that is, how does your idea of flailing connect with what we observe in the world as like good messiness and randomness, like the success of, say, simulated annealing and sort of like the ad hoc conversations that people have that are unorganized?
Yeah, that is a really, really core question for where I am right now. Thank you, Jay. So starting at the beginning, Fred said something a couple of weeks ago that if you can see it personally, we can probably detect it. If I can come up with a model of this is definitely it, what features are coming out of there. So yes, I think whatever model I have developed at this point is modelable.
And my question is, what is that? Like,
what is that model?
What do you think looks like the flailing?
I tried, so there is a lot of literature actually to pull from on this. And I have a big pile of it that is not in this, that I was waiting to see how the dive into our actual data was best applied to it. So the stuff that Mike was talking about with sustained unproductibility, that's going to go right back to the top of the pile for reassessment, which I think got mentioned, but I didn't catch that important detail of, no, our thing didn't really work, but maybe if you were a more constrained environment, there's some lessons to be learned there that I didn't catch on the first read. So I'm going to go back through.
So one answer that you're giving, Jay, is sustained unproductivity.
So but then there's the definition of productivity. So like you're pushing the predicate down the road a little bit with that. And a big thing that I did a lot of was I was reading a lot of Perkins, and he talks about tinkering often as a negative, but it's actually a pretty neutral term. It can be good, it can be bad, and explored a lot of that with this age group of students. It was like 1985 at the time, and the tools were different. But Perkins has a lot of things to describe succinctly what happens when they hit problems. And that wasn't quite right either, but it was the basis of my model. So my model in my head is sustained unproductibility is a great term to describe it. And productivity. Sustained unproductivity versus getting back there on its own. Because I was not expecting the packets to change size of flailingness.
That's kind of like a big meta level thing.
Yeah.
But
It's.
I feel like
I'm trying to answer with where the answers came from, but like.
If I stood behind a student and I didn't talk to them and I wasn't running the interpreter in my head, I think most of us think that we could tell if they're flailing. And
Yes.
we're looking at like very physical, gross motions of like, they're putting in blocks, they're adding new ones all the time, then they're deleting them, they're moving things around. We can tell that there's no reason behind it.
So.
Or is that the kind of that's bias?
That's it. So my big idea, now I think I understand what you're going at better. So my big idea really was to build this model. I'm intentionally using a word nobody else is using, of flailing. That doesn't have a canonized definition behind it because I want to try to build that definition based on that sense, that expert sense of anybody could stand behind any one of these kids and watch and be like, well, you clearly don't know what's happening, or you're figuring it out, you'll get there, as two different things. And I sort of want to create that model. Now, what I'm using for that expert opinion, I'm not sure how to describe that to you at this time. I'm not sure how to express that. But it's definitely going to create thoughts.
Yeah, so one point here, you may like to consider possible measures of entropy kind of thing, where you can measure, if you could measure it for a system. So if you can make it in a kind of a graph and you find out, measure the entropy of that subgraph, probably that could be one reason. But whatever you do, you probably have to consider the third part, the quantitative descriptor of degree of flailing, which you mentioned. That's a great point you have in your slide. So that's a critical part. So the entropy is one possible, but whatever you do, you have to probably consider the measure how far from you are from the ideally either from the goal or from a specific center point.
Right, so that gives you like a sort of a literature distance, like a code distance. That's used in some learning analytics stuff of saying, here's a solution, what's the code distance from that?
Either from the goal or from the point where you are. If you are going from that point, then it's an entropy measure of the system, the entropy of the subgraph, or else from the goal. Maybe you can consider these two ones.
That would be it. So distance from, and does your distance from change over time can be how you can predict, or how you could assert that that person is sustainably not going anywhere because their distance to goal doesn't change. Is that sort of how?
Or it's cyclic.
Or it's cyclic. It changes but keeps going back. Yeah.
Right, that's something Mike raised, is the patterns that are like you keep getting, you're stuck through a series of gestures that are bringing you back to where you started.
Yeah, and the thing is that it might not always be the same action, but it's a group of things, right? And what's interesting, at least with our work, and I think Mark might find it too, is that things that on the surface might actually seem like they're productive, actually probably aren't when looked at like through a better lens, right, of understanding what they've maybe done before.
Perkins hit on that really hard, that the kid could be driving up the wrong hill and trying really hard to
Right,
continue to
I love that idea of
optimize.
the local maxima, which is actually the wrong. I read you mentioned that, like it looks like they're at the top of a hill, but it's the wrong hill.
It's the wrong hill. It looks that
That's really nice.
Perkins, one of the core things from Perkins is unproductive tinkering is particularly insidious when you look like you're close to the solution.
Yeah.
When it looks like you're almost there, but really you're totally not. That you keep like trying to hack at that last like little bit of change, but it turns out that ladder is maxed out. You're never going to get higher. You're never going to make it. That's why that comes up and is so interesting because in that model.
But again, but like the thing that's weird about that though is that in most systems that we know about, when you reach local maxima, doing random things that you can't justify is the way of getting out of that. So I think of flailing as being a student not understanding what they're doing, but when I look at like hill climbing algorithms, they fail for local maxima and they are doing a logical thing, as opposed to jumping around is what actually works.
I had trouble with the climbing up the wrong hill, because if you're climbing up a hill, that's not random. You're doing something intentional to climb a hill. Maybe it is the wrong hill.
Right.
But that's not like you have no idea what you're doing.
I'm sort of overweighting Perkins for the
Yeah.
general discussion.
Right.
But what they were saying was it's one of those outcomes in that paper, again, 1985, that the tools that we're using to discuss were not there yet. Not machine learning tools, but like understanding of cognition and education kind of tools. The student has a hard time identifying that the approach is wrong. That's harder to do in App
Top of the
Inventor.
hill and you fall down, you keep going back, and you don't
Right, they're
realize
not,
that
if they were to flail harder, if they were to flail so hard they fell off the hill completely, that could be better.
Right.
And that's sort of one of the factors here of, I don't know how that's going to play out yet. But looking at center point or goal distance as a meta descriptor might do that. I mean, maybe that might
How
do that.
many? See, I saw you had 3 sets of blocks that you showed us. That you could have showed us. You showed us 2 of the 3.
Yes.
So presumably you could tell a story about the third one. How many have you gone through that you could tell? Like you knew where the long story, the one that had like a couple 100 blocks. You knew where it was going. You had looked at it. How many of those have you done it for?
About 15.
Oh, that's a reasonable number.
Yeah, I extracted those 3.
Yeah, right.
I look at it in the
So-
interface live. I don't have to extract them all to images. I did that for you.
So you showed us 2 of the 50. One was a kid moving straight to the goal. The other was a kid meandering, getting at the end, but we're not sure if somebody jumped in and gave them the answer.
Yeah, I'm pretty confident they did, but I can't say that.
All right, so good. So what are some other patterns that you saw out of the 50 that you looked at?
A lot of 15, not 15.
15. Oh,
Oh,
okay.
that's why you're so impressed. Yeah, 15. The biggest pattern is repetition, seeing the same state over and over again, doing stuff and throwing it away. Part of it is the nature of App Inventor's blocks. I see you, Dan. I'm trying. The nature of App Inventor's blocks make it very easy for you to just throw whole chunks of code away and start over. One thing that comes up a lot is introduction of extraneous blocks that are not relevant to the solution. And because that puts you on a wrong hill, that they play around with that for a bunch of time, but it was never the right block. It will never do the right thing until they eventually give up on it, come back down that hill, throw it away, start over, and then you're back at an earlier state. So it's exactly the kind of thing. So the Markov model might expose that cycle. The distance to goal measure might expose that cycle. But those are the cycles. It is cycles that's
Pulling
coming
out
out
the
there.
wrong block would move you like away from the goal, right?
Correct. Because it puts you on a hill that you're then going to invest time on that's never going to pay off. What is not in the proposal manuscript at all is this concept of identifying these cycles of meta descriptors. Because that's new as of this last phase analysis, which was like the last week. And this discussion was perfect to like embody with the tools. Dan.
I think you mentioned this earlier on, but could you remind me what role, you said you're going to do a statistical analysis, like an ANOVA or something. What role does that play in this process?
That's sort of a quick indicator of what looks relevant. It's not intended to be the answer, unless something comes back really strong. It's sort of a might as well try, to be perfectly honest.
So do you know like what the dependent or the independent variables you're feeding into that are, and like what your hypothesis?
I ran a few things that I developed. It was like a month ago at this point. I'm trying to remember without having to actually open up SPSS for you. The independent variable is population, which is the handpicked, like you flailed, you didn't. And to run that for real, I need more of that. The dimensions that are going into it have been number of types of changes. So it's archetypal type of changes. There was all based on how many code-based changes did you have, how many visual-only non-code changes did you have, and where did you spend your time on those? Various ways I package that data together to actually run it. And thus far, I've only done it in aggregate per student project. So a person doing the debug activity is then one number of I made 15 code changes, I made 45 visual only changes. How does that look against the population? So very, very simple stuff.
The hypothesis you were testing?
Oh, the hypothesis I was testing was that the number of the density of those changes is dependent on, has the null hypothesis is those have no effect on whether you were flailing or not. The right way to say it. Evan.
Well, I've got a whole bunch, so maybe I'll just cover a couple and I'll send you an email. But
That's great. That's great. Thank
so
you.
the first is that earlier on you showed a bunch of statistics, and there were a couple that I thought might be important but were missing. I'm not sure if you collected them or not.
I
First is-
probably did. That was just sort of fun for the audience. That wasn't
Well,
like
so one I was
the
thinking
research
of that
list.
Could be important is gender, because at the age of 4th to 6th grade, you might see differences between males and females in terms of their ability to structure and think about things logically. So if that's not in your model, it should be. At least only see if it really has no effect.
I would love to. I can't have that.
Because I think that might bother
We don't
you.
have that information.
We don't have that, and they are actually quite specific. I'm not allowed to have it, even if we do, because the IRB didn't clear it.
So the second is you mentioned that you have a long tail in the distribution.
And I did so, and in the same breath showed you a median and an average very close together.
Yeah. Well,
So you're just gonna have to believe me because I snipped edges of that in advance.
Well, sure. Well, my problem then is really more with the ANOVA, right? And this idea, if you know that you have a long tail thing, are you going to do almost elasticity tests? Or are you going to do a log normal transform? Because ANOVA assumes that your data are normally distributed. So if you've got a long tail, you need to do some sort of non-parametric.
Yes, I have an answer for that, which is the tail goes away. A lot of the corrections we were talking about, of if they opened it the next day, I need to not count that. If it was trivial, if there was one change, they didn't do the activity, they just opened and closed it. After those sort of corrections, the data is a lot more normal.
And does that also include this idea of doing the 15-minute cutoff? Or?
That will be included in that class of correction.
And then
That shot Dan's hand up.
just
So.
very- yeah, well, just quickly also, so you were talking about
Do-
doing the ANOVA to detect whether they're flailing around. What about something like logistic regression, which ties in a little bit to Mike's question before of how do you?
That's actually a way better test, admittedly.
I was gonna ask if you had looked at doing like an exploratory factor analysis.
Yes, I have looked at that. That has come up over and over and over again. And I'm actually really surprised I didn't put that on the slide because that's like a major piece of the notes. Going to write it down again. See, this is why we're here. This is why we're here.
We have a couple questions from the web.
Oh, yes.
From Daryl. So, yeah, couple questions from him. Do you have any data on running the program, sensor input? That sounds like it would be very useful info, a little bit late now if you didn't instrument for that. Question 2, how specific is the flailing detection to the specific given task, i.e. can flailing detection be generic? Or must it have prior data for that particular task? Returning to a prior state could be detected if you can build states dynamically as they're working.
Yes. All right. So to start off, what was the first one?
The first one is, do you have any data on running the program sensor?
Oh,
input?
yeah. The runtime was not instrumented.
We thought about it.
We thought about it really hard. My data collector has the hook open for it. But we weren't able to instrument the actual runtime. So we don't know what the student was actually doing with their test device. We only know what they were doing with the programming environment on the computer. So they could be testing the same thing over and over and over and over again, and we don't know. We just know it took 4 minutes. And we have no idea if they went to the bathroom or if they were testing rigorously. We can't know. With that, it turns a lot into what I have the poster right outside about, the testing and iteration patterns, which was my master's work. So that would have been fun, and we wanted to. It didn't happen.
And the second question was, how specific is the flailing to the specific task?
That's already showing to be something. And that's sort of another question to deal with as we do this. I think the more powerful models will be better at it, because if you're doing something like a distance to center point or distance to solution, you end up with sort of building the answer in. And I'm really not sure. That's right on the edge of I don't know yet. But there are definitely differences in the number, just in looking at number of snapshots per project, they're a lot higher in the temperature activity in general for across the board.
Let's take the last question from Mike here.
Okay, well, this might not be the best last question, actually, but,
The committee will continue after you.
sure. Do you have any data about what's happening off the screen? So like, do you have any video recording stuff? Do you have, because one of the things that's very interesting often in these sorts of cases are, do kids talk to each other, right? Did they, you know, what was happening in the room? Because I don't know the design enough of like, but one of the things might be that the kid is flailing and another kid sees it and gives a piece of advice. And that was the thing that helped. And often that can be really valuable data to know about and also can help inform, especially if you're looking forward to like, how do you help, you know, the ways of nudging versus telling and those sorts of things could be very valuable. Like additional data and understanding what's going on in your model.
So the easy answer is a hard no. The slightly more nuanced answer is there were lots of people in the room and I was able to collect some observations day of. That's how we ended up with this small list of known conditions. That came from ground truth, real observation at the time, written down. It is my greatest failure thus far that did not extend to the entire population. It was my intent to, and it didn't work out in the fray of being in a classroom. Yeah, we got a couple of them though. We got a couple that came back from the teachers of high, low, I don't know. And that's what I've been using as sort of the dipstick points to see if I'm insane or not. But no, we weren't able to do that.
Thanks very much for coming.
Yes, thank you so much.
Conversation. Thank you. Thanks a lot.
I didn't put my email on the slide, but I think everybody here can easily access me.
Please take food on the way out. And
Yes.
Jay, can you stay for a few more minutes? And Lynn, you still there?
Absolutely.
All right, I am going to say thank you to everybody on the live stream who's watching at home, and I am going to conclude our broadcast. Thank you, Mom. All right, thanks everybody. And, have a great day.
Mark,